Have you ever experienced that heart-stopping moment when your car glides across a wet road? That terrifying instant when your tires lose their grip and suddenly you're no longer in control. Or perhaps you've pushed one of these massive granite spheres or Kugelballs at a museum, some weighing several tons, yet they can be rotated with just the touch of a finger, even by a child? What if I told you the same physics that makes your car hydroplane also powers some of humanity's greatest engineering achievements? How is this possible? The secret lies in an incredible engineering of hydrodynamic lubrication, which occurs when a thin film of fluid, whether it's water, oil, or even air, gets trapped between two surfaces. This fluid layer essentially eliminates direct contact between the surfaces, dramatically reducing friction. In the case of those museum Kugelballs, a thin layer of water is constantly pumped between the sphere and its precisely shaped socket. The pressure in this fluid film fully supports the weight of the stone, allowing it to rotate freely in any direction. Similarly, when your car hydroplanes, water forced beneath your tires creates pressure that lifts your vehicle completely off the road surface. The tire and road don't actually touch. They're separated by a thin water film. That's why you lose control. Your tires are literally floating on a film of water instead of gripping the road. But perhaps the most extraordinary application of this principle sits quietly at the Holtwood hydroelectric plant in Pennsylvania. This power plant was built in the early 1900s. It was one of America's largest hydroelectric facilities, but it was struggling with a critical problem. The enormous bearings supporting their turbine shafts were failing after just 2 months of operation. These frequent failures created dangerous maintenance situations, costly downtime, and unreliable power generation, a disaster for a facility meant to power homes and industry across the region. Before we jump into how Kingsbury solved this problem, I want to give a quick shout out to this video's sponsor, JLCMC, your go-to mechatronic marketplace with over 600,000 parts, aiming to provide one-stop service, global delivery, and industry-standard high quality. Their prices are way better than what you'd find at most online or retail stores. Plus, if you're new to their site, you can register today and snag $60 in coupons, along with access to their monthly coupon. Now, let's get back to the topic. In 1912, Albert Kingsbury, a professor of mechanical engineering at the University of New Hampshire, had the opportunity to design one of his first practical application, and probably one of the most remarkable thrust bearing he ever made, for the Holtwood hydropower station on Susquehanna River. The Kingsbury's oil-lubricated thrust bearing was designed in replacement of a roller thrust bearing for a water wheel-driven generator of 12 megawatt, rotating at around 100 revolutions per minute and supporting a load of approximately 220 tons. Kingsbury's bearing consisted of a series of stationary tilting pads arranged in a circle. As the shaft with its collar begins to rotate, these pads tilt slightly, creating wedge-shaped gaps. Oil flows into these gaps in a way that generates enormous pressure, enough to completely separate the metal surfaces, resulting in negligible friction and bearing wear. Astonishingly, the bearing was rated to continue operating maintenance-free for 1,320 years. Not decades, not centuries, but more than a millennium of continuous operation. In 1950, after 38 years in operation, the generator was rebuilt, but the thrust bearing was in the same perfect condition. In 1987, after 75 years, the Kingsbury thrust bearing was still working flawlessly and was officially designated by the American Society of Mechanical Engineers, ASME, as an International Historic Mechanical Engineering Landmark. In fact, it's still running today, over 110 years later. Kingsbury's invention was unprecedented and didn't just transform one hydroelectric plant. It sparked a revolution in large-scale machinery. Today, his groundbreaking design supports some of the most demanding applications on the planet, from massive hydroelectric turbines to nuclear submarine propellers, from wind turbines to industrial compressors. What started as a solution to a single engineering challenge has become a cornerstone of modern technology. What do you think about the future of bearings? Share your thoughts in the comments below. If you liked this video, hit that subscribe button for more explanations of the world around us. Thanks for watching.